Hello and welcome to my video, week 1 in a nutshell, DNA, chromosomes, and karyotypes. Welcome to the semester. Hopefully it hasn't been too overwhelming for you so far. If it makes you feel any better, in my opinion, after weeks 1 through 3 and maybe 5, it gets easier. So you guys are actually doing the hardest part first. So bear with it, you can survive. We're just laying down the groundwork this week so that you can understand the cooler applications in the future. So let's get started. Let's see if this video can help you understand your readings and the material better for this week. Hopefully I'm able to explain it in a way that makes sense for you. So let's get this title out of the way here and let's get started. Okay, DNA is an acronym that stands for deoxyribonucleic acid. It's a mouthful. Deoxyribonucleic acid. You can see why we abbreviate it as DNA. The purpose of, or what DNA is it's a molecule inside your cell that stores information. The specific information that it stores is how to build a cell. And by extension, how to build an entire organism, such as yourself and myself. So it doesn't really do anything other than store information, but because of the information that it stores, it's one of the most important molecules in your entire body. Because without it, the cell wouldn't know how to build itself or how to survive, and the cells die really, really quickly without DNA. So DNA is very, very important. And it turns out that DNA is such a resilient molecule, it can do all sorts of kinds of things. Not only can it provide instructions for how to build all kinds of different creatures, humans, plants, animals, mushrooms, it also has the ability to do different actions within one organism. So let's look into that here. In your cell, there are 3 different types of DNA. We call them regions, different areas of the DNA that do different jobs, that have different roles to make the whole system work. The 3 major areas here are called the genetic region, the red on this one, the regulatory region, and the junk region. And legit, that's the scientific name for it. It's called the junk region. Okay, genetic regions regulating your cell is made up of these 3 regions. And when we write it like this, we make it sound like a third of your DNA is the genetic region, it's all together, and a third is the regulatory region, etc. But really, there are different these are all scattered throughout. So there are several genetic regions and several regulatory regions and several junk regions, and they're all interspersed and spread out throughout your DNA. But we'll talk about their general functions here. Genetic regions, their job is to hold the information that tells you how to build the cell. So I told you that was the DNA. This is the specific part of the DNA that does that. So instructions to build a cell. Specifically proteins that we'll put in more detail in week 5. The genetic regions contain the instructions on how to build a cell. So in week 5, we'll learn how the cell can use special proteins to read the genetic regions and build proteins based on the instructions contained in the DNA. Genetic regions have these special pieces in them. They're the specific instructions pieces that are called genes, hence the name genetic region. And the genes are the instructions to build the cell. There are thousands of different genes. The human body has about 23,000 genes in there. And each gene is a recipe of sorts to, because the DNA works so nice with recipes. If you think of a recipe has instructions on how to make a pie or something like that. Well, a gene is like a recipe for a protein instead. Each protein is different and has a different job in the cell, and so each gene is different, specifying for how to build a different protein. And again, we'll go into that more in week 5. So the genes are the recipe for how to build the specific protein components of the cell. And those are in the genetic regions. Okay. The regulatory regions, these don't code for proteins. They don't have instructions on how to build proteins. They don't have instructions for how to build the cell. To think of this like a light bulb. If the genetic region is the light bulb, we want to, in your house, you want to control when you have the lights on and when you have the lights off. Because if you have the lights on all the time, you're going to waste a lot of energy because you don't need the lights on, especially during the day or maybe in rooms that you're not in at that current moment. So we don't want to be making proteins off of all of the genes in the entire, or in all of your DNA all the time and in vast amounts. So the job of the regulatory regions is to tell the cell when to build or to read certain genes, when to build it, going to the recipe analogy. If you, we have certain foods at certain times of the year and in certain quantities. We have turkey on Thanksgiving, for example, and people don't usually cook a whole turkey on any other day of the year. And so we would want to control to make sure that we only cook a turkey on Thanksgiving and not during the rest of the year. And if we're only having 4 people over for dinner, we don't want to cook 40 turkeys because nobody's going to be able to eat 40 turkeys. So we need to, the regulatory regions help control when we make the genes, or when we make the protein from the genes, control when and how much of a protein is made. That's their job. And we will learn more about the regulatory regions in week 11. So we will come back to that. These first few weeks, we're going to focus mainly on the genetic and junk regions, but we'll come back to the regulatory regions in week 11. These third ones are the junk regions. And as their name implies, their job is, as so far as we know, to sit there and look pretty. It has no function for the cell whatsoever. There are a few exceptions to that rule that I'll cover here in a sec, but the junk regions, they have no information to build proteins. They don't control when or how much of a protein to make. Their job is to just be there. So you actually have junk DNA. In fact, most of your DNA is junk. Most of the DNA in your cells has no perceivable purpose at this time. So no purpose. It's just there, hence the name junk region. Well, it turns out that there are 2 different kinds of junk region. And in order to do this, in order to help understand this better, let me use a little analogy here. And let me pause the video here to bring up the analogy diagram here. Okay, here we go. I like to use the analogy, again, continuing with my recipe analogy, I like to use the analogy of online food bloggers. And I just think this is hilarious. It allows me to poke fun at them a little bit too. if you've ever gone to like a website, this is a little mock-up one that I did, again, poking fun at them. If you've ever been to get an online recipe, you'll notice that all of these recipe bloggers have a standard format on their website. They've got like the title and whatnot, and then they've got the name of the recipe, and then like pages upon pages upon pages of explanation of how fantastic this recipe is and where it came from, and how your neighbors won't be able to resist diving through your window to eat it all before you finish cooking it, or something like that. It's always hilarious. And nobody ever reads that. Everybody always skips over it. And they're like, come on, scroll down, scroll down, scroll down, get to the recipe. And then the recipe, they're like, okay, there's the instruction. That's finally, thank you. And then afterward, you've got pages and pages of comments. Let me bring up my annotations here. Drop. Okay, yes, good. Okay, yeah. So we got the recipe, and the recipe is, your standard recipe has instructions. So there's like all the ingredients that you've got up here, right? DN. Oh, that looks fantastic. Ingredients, and they've got like several different ingredients here. And then like instructions, right? It's your standard recipe. 1, 2, 3, etc. There's writing down here. And by following the recipe, you're able to make whatever food that they've been praising in the previous paragraphs. Below the recipe, there is, oh, my annotations bothered me. There's like comments, a comments section down here that nobody ever reads either, usually because they're depressing or non-trustworthy, but that's just me. Okay. In this analogy, the junk writing that's before the recipe and the junk writing that's after the recipe is our junk DNA. So this stuff up here, oops, this stuff up here and this stuff down here is junk because it makes no contribution to your pie. It doesn't have any instructions that are useful to being used in your cooking efforts. Its sole purpose there is basically to bore you. And so that is our junk region. And then we've got the genetic region here. The recipe would be kind of like your genetic region. So that's your genetic region. And I suppose that I don't really have a good analogy as part of this for the regulatory region, but the regulatory region would tell you like up in here, maybe it would tell you only make this during Thanksgiving or whatever, like it says the particular type of food and what kind, those little instructions up there. That would probably be your regulatory region up there. Well, it turns out that if you've ever gotten a recipe online like this, the advertisers are fantastically good at getting everywhere. Like you've got ads up here and things like that. But they've got usually smack in the middle of your recipe, there's another advertisement for like Clorox or something like that. They cram advertisements smack in the middle of your recipe. I don't know if anybody else gets frustrated by that or not, but you got an ad which is also junk, because if you've got a Clorox ad smack in the middle of your recipe, you're not going to add Clorox. You skip over it because Clorox would ruin your pie, right? So you skip over it, you ignore it, and you read the rest of the recipe that's actually important. That is also junk DNA, but notice, or junk DNA works the same way. There is actually junk DNA both outside of the genetic regions and smack in the middle of a gene. And so because there are two different kinds of junk region, we have to have two different names for it. Because we're scientists, we have to have names for everything. So this outside, or so the areas of junk DNA that are outside a gene are called satellite DNA. because satellites orbit around things, right? Like a satellite around the Earth. And so satellite DNA is junk DNA that surrounds the genes. It separates them. So it's not actually in the gene, it's just around it, taking up space. The second kind is this junk that is smack in the middle of a gene, like this Clorox ad smack in the middle of my pie recipe. Those are called introns. INTORNS. An intron is junk DNA that is smack in the middle of a gene. And we kind of glaze over what happens to the introns in this class because it's really, really complicated. But the cell has methods of, when it goes to read the gene to make a protein, it has methods of ignoring the introns, so that only the recipe, only the good recipe components are incorporated into the protein. And we'll again cover that more in week 5. But there's your general idea. So if we switch back over to here, so the junk regions, there were those two sub junk regions. It was satellite DNA and introns. Satellite DNA is junk DNA that is outside of a gene, and introns are junk DNA that are in a gene. And I like to remember that, like in is inside, whereas satellite is around. So yeah, there are your 3 regions of DNA, the 3 kinds of DNA that make up the DNA inside your cell: genetic regions, regulatory regions, and junk regions. Okay, let's erase this and move on to the next topic here. So believe it or not, if you take all of the DNA in your cell, or in one of your cells, and strung it out end to end, you would have about 3 feet of DNA in every cell. That's about 1 meter for those of you that aren't in America. 3 feet DNA in every cell. Now, if you think about DNA like a thread, you got 3 feet of thread that you have to try and fit in a nucleus about the relative size of a pinhead. So basically, we're trying to cram 3 feet of string inside of a pinhead. That's extremely difficult. So we need to be able to compact the DNA down. I like to think of it like yarn. Yarn, if you just let it sit out, then it just gets all over the place and it takes up all kinds of room and it gets tangled and all sorts of things like that. So how do you fix the problem? Well, you wind it up in a yarn ball. You take all of that yarn and you wind it up really, really tightly into this little tiny yarn ball that you're able to move around and it doesn't get tangled and everything like that. And then you're able to unwind just the amount of string that you need to be able to knit your sweater and leave the rest of it in the ball. Same thing with cells. We're able to wind up the DNA and we're able to compact the DNA and have some parts of it be uncompacted so that the cell can read the genetic regions and work on the cell, and have other parts like the junk regions compacted so that they take up less room. And overall, by compacting it all, I'm able to fit it inside the nucleus. Now let's show you how. It turns out that the cell, in order to better organize in order to better organize the DNA, cells have split the DNA up into big long pieces of DNA called chromosomes. So a chromosome is just a big long string of DNA. And it's got genes on it and all sorts of things like that. And that's an oversimplified definition, but that's basically what a chromosome is a big long string of DNA. I got this great big long string of DNA. In humans, we have 46 of these. So there are 46 pieces of DNA inside every nucleus. of every cell in your body. And we'll go and explore more about those later. So each of these pieces, we need to be able to compact them. And so since thread can't really compact itself, we need to have some protein helpers. And there's two of them in particular that we ask you to know about this week. These proteins, I'll draw them here as circles. They're spherical or cylindrical in shape. These are called histones. Histones. Histones are proteins that their specific job is to act like a spool for the DNA to wrap around. So the DNA comes into these histones every couple dozen bases or so, comes in and wraps around the histone. I think it's 2.4 times, but you don't need to know that. It comes out here and it wraps around this histone, comes over here, wraps around this histone, etc. Well, that was awful. Wraps around the histone. So we string up these little histones. Now notice I was able to cramp, by winding it around these histones, I was able to fit way more DNA on my page than I was able to by drawing this line down here. By drawing the blue line around here, I was able to fit more DNA than I was down here. So already the DNA is taking up less space simply by winding it around the histones. Now let me show you pictures of this, because this is, in my opinion, I think it's great fun to see the pictures. Let me go grab the picture quick. All right, here's the picture. This is a really powerful photograph. It turns out the DNA is too small to be seen using light. So no matter how powerful your light microscope is, you're never going to be able to see DNA in its unwound form. It's just too small. So we have other microscopes called electron microscopes that use different methods other than light to be able to create pictures of things that are even smaller than you can see with a light microscope. Well, this is one of those pictures created with an electron microscope. Across the middle here, let me draw here. So these bumps here, you'll see, these are histones. All the way along there, all of these big thick bumps here are histones. And this blue line going across the middle here, wrapping around each of these, etc. It keeps going all the way across the page. You can see it right there. Oops. That's DNA. So there you go. That's a real life photograph of DNA wrapped around histones. So notice there's one every couple of, there's a histone every couple of 100 base pairs. And yeah, we just string them out. It looks kind of like beads on a string. So that's usually the term that they use when describing histones on DNA, is they call them beads on a string. Anyway, I just thought that's fun. I like to point that out. Let's go back to the drawing here. Okay, here we are. Now, wrapping it around these histones takes up or shrinks the DNA a lot. It compacts the DNA an awful lot, but it's still not enough. We need to be able to compact the DNA even further in certain circumstances, such as dividing a cell. When you need to divide a cell, you need to compact the DNA as tight as you can. Just like when you're moving houses, you want to pack all of your stuff up as much as you can inside these boxes so that you can move the boxes, because they move easier, rather than taking each item individually, and you'd have to use half the ward an entire week to get it done. So you've got, so we need to be able to have help beyond the histones in order to compact this even further in that circumstance. So there's the second protein that we ask you to know for this week. It's a V-shaped protein, and scientists are still trying to figure out how it does its job. We know what it does, and we think we have an idea of how, but we're not quite sure. It's actually quite fun. Turns out scientists don't know everything. This protein is called condensin. Condensin. And condensin, its job is to come in here and grab onto the DNA at periodic intervals and then pinch it closed. So basically the idea is to grab areas of DNA and bring them closer together, wrap them around each other, get them all nice and packed around. So the histones, it's wrapped around the histones, and now I'm winding histones around histones kind of thing. So the idea of the condensin is to pack it even further. In fact, that's why it got its name. Here's a little fun fact of enzyme naming rules for you, or of protein naming rules. If the name, with a few exceptions like histones, this is just a general rule, if the name ends in IN or ASE, it's a protein. And everything before the IN or the ASE says what the protein does or what it's associated with. If you want to learn more about that, I have a little article on my website about enzyme naming rules. So condensin is a protein that condenses things, hence the name condensin. That may help you remember that that's condense's job, is it helps condense the chromosomes. The way I remember histones is I just think of stones and these little rocks that it wraps around. That's how I remember that one. I don't know if either of those will help you. But so condensin helps condense the DNA further than the histones can do. And the job of the histones is to act as spools for the DNA to wrap around. So that's how we condense it down. We condense these chromosomes down so that they fit inside the cell, and condense them down even further with the help of condensin in order to split or to separate them, move them around to other cells when we're splitting the cell and making new baby cells, which we'll learn about next week, how you do that. So when you compact a chromosome down fully, erase this here. We take this big long string of DNA, we compact it down, and it actually gets so dense, so well packed, that you can start seeing it in a light microscope. And they look usually like the letter I. They're like a big fluffy stick. So that's what a chromosome looks like when it's fully condensed. And it's got, there's a couple of special features about these things that I'll show you here in a sec with a real photograph, but let me focus on two areas here. There are two special areas of a chromosome to know about here. First is right here in the middle, there's a little pinch you can see, and it's not always in the middle of every chromosome. Sometimes it's up near the top, but there's a pinch called a centromere. Now the centromere is in the middle, and its jobs, it has two jobs. One of the jobs we'll learn, or both jobs actually we'll learn about next week, but its job is to link chromosomes to their sister chromatid, which we'll learn about next week. When you copy the DNA, it hooks two chromosomes together. And it also helps play a part in splitting the cells, like in mitosis and meiosis. So again, we'll learn more about the centromere next week. Just know that the little pinch area is called a centromere. The other important part at this scale is on the ends. On the ends of the DNA, there's junk DNA out there, lots of junk DNA. So it's satellite DNA. And this particular satellite DNA on the very, very tips, they're called telomeres or telomeres, depending on what part of the country you're from. Telomeres are located on the ends of the chromosome, and their job is to protect the chromosome. It turns out that being a chromosome inside of the cell is actually kind of an abrasive experience. And we have to keep our chromosomes inside a nucleus because there are proteins outside the nucleus whose job in life is to destroy DNA by chewing on it from the ends. So the job of the telomere is so first we keep it inside a nucleus, and then just in case we put these telomeres on the end to make sure that nothing bad happens to your chromosomes, because we don't want your DNA getting chewed up and shredded up, because that's bad. that would get you killed real quick. So that's one of the jobs of the telomeres. The other one is that it turns out in the process of replicating your DNA, as you get older, you divide your cells and you replicate your DNA over and over again. Every time you replicate your chromosomes, they get ever so slightly shorter. It's not discernible from this far out, but you lose a couple of bases of DNA off of both ends every time you get it. So your chromosomes are getting shorter. Now, if you had genes clear out here on the ends, then as soon as you were born, you would start whittling parts of the recipe away. We'd start whittling ingredients off of your recipe, and now all of a sudden you would look at your recipe to build your pie and forget you have to put in water into the pie crust and things like that. Very important things. And suddenly, so rapidly, it would kill you because every time your chromosome got shorter, it would ruin the recipes more and more until it killed you. That's bad. So by sticking junk DNA that we don't care about, that has no impact on the cell, on the ends, we can afford to have the cell whittle DNA off of the telomeres, off of this junk DNA, because we're not harming the actual important stuff here in the middle. And so basically these act like a fuse on your life. Scientists predict that humans on average should be able to live maximum about 120 years because depending on how many times your cells divide, that's about how long it takes to whittle through the telomeres. And then you start knocking important stuff off, and that's when it becomes difficult to survive longer. So the telomeres are kind of a fuse that help keep you alive simply because they're expendable. And they help protect the chromosomes from being chewed up. Yeah. So those are the telomeres and the centromere. So good so far. We'll move on here. Let's go look at other features of chromosomes. Let me switch over here to my picture. Over here. Okay, here we go. Okay. In order to be able to see the chromosomes, scientists wait until the cell is ready to divide, which means it goes in and compacts its chromosomes down all the way, and then we stop the cell and pop it open. I know we're jerks. We let it get almost there, and then we kill it. And we pop the cell open and drag all of the chromosomes out. So we drag all of these fully compacted chromosomes down, and then we sort them out because we're humans. We like organizing things. We sort them out based on a few things. The first one is size. So we organize them by size. Notice chromosome number 1 is the longest one. And then chromosome 2 is slightly shorter, chromosome 3, chromosome 4, all the way down to chromosome 22. And then there's these ones down here, and I'll explain that in a sec. So that's one of the ways that we organize them is by size. Now notice so there are 23 different kinds of chromosomes, 22 of the numbered ones, and then the sex ones down here. And you've got 2 of each one from mom and one from dad. That'll become important here in a sec. We'll come talk about how you name cells like this. So there are 2 of every kind. You got 2 copies, one from mom and one from dad. So these here, these 2 chromosome 1s are both chromosome 1, and we name them by numbers, so we call it chromosome 1, and then both of these are a chromosome 2, etc. Chromosome 3, chromosome 4, notice that they're basically identical. Well, it turns out that they're not identical. The 2 chromosome 1s have the same genes on them. You might think of them like a cookie cookbook, right? If you got a cookie cookbook from dad and a cookie cookbook from mom, they will both likely have a chocolate chip cookie recipe, and they'll both probably have a snickerdoodle recipe. I'm probably making you hungry here. So they all have the same genes, but not necessarily the same version of a gene. For example, like your dad and your mom, yes, their recipes could, your dad's side of the family and your mom's side of the family could agree that we will make a chocolate chip cookie with a recipe, but one of them may want to put more brown sugar in than the other. So there's not just one way to make a chocolate chip cookie. And so so these two chromosome ones, the one that you got from your dad and the one that you got from your mom, all have the same genes, but not necessarily the same version of those genes. The word that we use to describe a version of a gene is called allele. And I've heard people pronounce that allele or allele or whatever. It's an allele. And an allele is a version of a gene. So it's not like a physical thing. It's a gene, just what version of the instructions did you get? So that's an allele. So these two chromosomes have the same genes, different alleles. And we call them homologous chromosomes. Let me write that word out here for you. Erase this to get it out of the way. These are called homologous chromosomes. So homologous chromosomes. So the two chromosome ones are homologous to each other. What that means is they are similar but not identical. They have the same genes, but not necessarily the same version of those genes. So the two chromosome ones are homologous to each other. The two chromosome twos are homologous to each other, but chromosome 1 is not homologous to chromosome 2 because chromosome 2 has different genes. It's a completely different chromosome. Completely different cookbook. This one worries about different types of food. This one's the cookie cookbook. This one's the meat cookbook. So chromosome 1 is not homologous to chromosome 2, but the two chromosome 1s are homologous to each other. And we'll hit that more in week 2. That's just a good vocabulary word to know. Okay, so the way that we sort these chromosomes out, we create it as a picture, as you can see here. And this entire picture is what is called a karyotype. Write that down here. Karyotype. A karyotype. So this whole picture here is a karyotype. And a karyotype is a photograph of the chromosomes in their condensed state. That's what a karyotype is. And then, of course, there are three ways that we sort out chromosomes to order them like this, like how they became chromosome 1, 2, 3, and 4, and how we're able to arrange them like a karyotype. The first thing to look for, I already mentioned, is size. So we order them biggest to smallest, and then we put as per convention, because normally the X chromosome would fit right about there, if you're counting length. But because the X chromosome helps determine your gender, we put it in the bottom right-hand corner, along with the Y chromosome if you're a male, for easy reference, so that you can look at a karyotype and easily see, aha, this is a woman, because she has 2 X chromosomes. I'll address that here in a sec. So that's the first thing, is you arrange them by length. Chromosome 1 is the longest, chromosome 2 is the second longest, etc. The second thing that they use to help tell chromosomes apart is the stripes. Notice, for some reason that we have yet to understand, when you condense the chromosomes down and then stain them with a particular dye, parts of the chromosomes stain darker than other parts. So you wind up with these stripes. Notice all of the chromosomes here are striped. We call them bands, B-A-N-D-S, just in case my accent there hid that D. B-A-N-D-S, bands. And if you look, the two chromosome 1s have the same bands. There's a black line right there, a black line right there, white lines in between that. They have the same bands, same with the chromosome 2s and the chromosome 3s. Some of them are less obvious. But chromosome 2 has a different band pattern than chromosome 1 or chromosome 22. So based on the pattern of stripes on the chromosome, people that do this all day, every day are actually able to tell exactly what chromosome that is. Pretty impressive. I definitely can't, but other people can. The third thing is where the centromere is. So we're coming back to that vocab word here. Remember how I told you that the centromere was in the middle, but that wasn't exactly true? Well, here you go. Notice at the center, or in certain areas of these chromosomes, they have this little pinch that's just not quite as wide as the rest of them. On chromosome 1, it's right here. But on chromosome 2, it's not quite in the middle. It's up here closer to the top. On chromosome 14, it's clear the heck up here. It's almost at the top. 21, it's down here. 22, it practically is the top. So the centromere is on a different spot along the length of the chromosome for each chromosome. And so that's a third identifier that they use to sort out the chromosomes. So it's the centromeres, where the centromere is, the banding pattern, where the stripes are, and how big it is. And those three things help scientists tell apart the 23 different kinds of chromosomes. And then we are able to sort them out into a karyotype to see your chromosomes. Now there's a number of things that karyotypes are useful for. Specifically 4 main reasons that I can think of. The first one is it can tell you the gender of the individual that we took the karyotype from. Because down here at the bottom, these sex chromosomes help determine whether you're a male or a female. If you get 2 copies of the X chromosome, like this individual, you're a female. And if you get 1 copy of the X chromosome and 1 copy of the Y chromosome, you're a male. So if we scroll down to find a different karyotype here, let's see. Let me switch to my other. Give me a sec here. Here we go. If we do this one, notice this one's a female, but down here in the bottom corner, this one's a male. We've got 1 X and 1 Y. So that's one thing that you can tell from a karyotype, sorry, is the gender of the individual. If they've got 2 X chromosomes, they're a female. If they've got an X and a Y, they're a male. The second thing that you can tell from a karyotype is how many chromosomes they have. I know it seems really, really obvious, but because a karyotype is a photograph of all of the chromosomes from inside one cell, you can tell how many chromosomes that person has. Humans, we've got, if you went in and counted them, 1, 2, 3, there are 23 different kinds of chromosome and 2 of each. So humans, our natural number of chromosomes is 46. And I'll talk about that here in a sec more, but humans have 46 chromosomes. So a karyotype can help me see how many chromosomes this individual has. Your standard healthy human has 46. That's the second thing you can tell. The third thing you can tell from a karyotype is, I mean, this one kind of bridges off of the second one, is whether they're missing any chromosomes or they have too many. Because that actually can happen, and in week 9, we'll go into far more detail into the chromosomal disorders, but there are things that can happen during meiosis that we'll learn about next week that result in a kid having too many or too few chromosomes. And so by looking at a karyotype, you can see that. Let me pull up an example here. Over here. Notice on this karyotype, and sorry, it doesn't all fit on the screen here. On this karyotype, all of the chromosomes are normal, but down here, look, we've got 3 copies of chromosome 21, and I'm only supposed to have 2. So this person, by looking at this karyotype, I can see that they have 47 chromosomes instead of 46. So they have too many chromosomes. This actually having 3 chromosome 21s, that is Down syndrome. So by having 3 copies of chromosome 21, that results in Down syndrome. And again, we'll learn more about the diseases in week 9. But there's an example there where I was able to just look at a karyotype and diagnose a child with having Down syndrome before they've even started manifesting symptoms. This is one of the things that they do when, if you've ever had a child, they almost instantly prick the heel of the baby after they're born and take a blood sample. They're going to go make a karyotype, among other things, to check to see if the baby has any chromosomal diseases like Down syndrome, because they can tell that quickly. Another example of abnormal numbers of chromosomes is down here. Notice this person has all the normal chromosomes except they just have 1 copy of chromosome X and there's no Y. So they're missing a chromosome. This results in a disease called Turner's syndrome that we'll learn about in week 9. So that's the third thing that you can tell, is whether they have too many chromosomes or if they're missing any and which ones. The last thing that you can tell is escaping my mind at the moment. Give me a sec. Let me go hunt this down. I remembered it right after I stopped it. Is what species you are. Most people don't consider that, but different species, a species being like a type of organism, different species have different numbers of chromosomes. So humans, our normal number of chromosomes is 46, but that's not true for every other creature. Some plants have 16. Some animals have as few as 4 normally, whereas other animals have as many as 400. And the number of chromosomes that you have doesn't necessarily determine how advanced or complex you are. The creature that currently holds the record for having the most chromosomes is a butterfly from North Africa. And that's got 400 some odd chromosomes. We humans like to think we're a little above butterflies. So the number of chromosomes says nothing of your complexity. It's just a fact of life that evolves over time. So humans, our normal amount is 46, but if you saw a karyotype that only had 16 chromosomes in it, you would know that it's not a human, it's something else. That's the fourth thing you can tell from a karyotype, is the individual's species. So karyotypes are extremely useful tools, and we'll come back to them in week 9, study them in more detail. The last thing that's important for this week is the names of these chromosomal disorders. So not like the specific disorder name like Down syndrome or Turner syndrome, but we like to refer to cells based on the number of chromosomes they have in there. And we use some special terms to do that. So let's come over here. I find that using a little table helps me understand these these words here. So let me show me the typing here. Here we go. So on this table, across the top, I'm going to put 2 suffixes. So it's the last half of the word. What we're going to do is assemble words here. So Somie is one, and the other one is Ploidy. One of my favorite words to say in the world. I mean, whoever came up with that, Ploidy, so much fun. Anyway, Ploidy. So Somie and Ploidy, they're across the top. And down the left-hand side, we're going to do the prefixes. So the first half of the word. And each of the prefixes is a Latin prefix for one of their numbers. So, mono, Somie, so mono, di, because mono means 1, di means 2, tri is in like a tricycle, means 3, tetra means 4, and you could keep going, penta, etc. But we'll just stick with these 4 for simplicity's sake, down the left side there. Now, let's focus on the ploidy column over here. A ploidy when something is ploidy or ploid, the term is referring to all of the chromosome types. So every chromosome pair. Basically what we're doing here is a math problem. So this says a number, and the end of the word says how many chromosomes does it apply to. So if it's ploid, that means this number at the beginning applies to all of the chromosome types. So the way that I like to think about these is determine what the creature's ploid is. I totally made that word up, but each creature has their own ploid number. And what a ploid is, a ploid is equal to the number of types of chromosomes, types of chromosomes that that creature has. So like that plant that had 16 chromosomes normally, they have 2 copies of every chromosome, so that must mean they have 8 types of chromosomes. So that plant would have a ploid number of 8. For humans, we have 23 different kinds of chromosomes, so a human's ploid value is equal to 23. So our ploid is 23 because we have 23 different kinds of chromosome. Now the prefix mono means 1, di means 2, tri means 3, tetra means 4. When we're doing ploids, it's a multiplication thing because we're saying how many of every kind of chromosome do we have. So if you are diploid, that means you've got 2 of every kind of chromosome, so you do your ploid, which was 23. For humans, it's 23 times 2 is equal to a diploid number of 46. So human cells and most every other creature are called diploid or diploid because we've got 2 of every kind of chromosome. Like up here, we've got 2 of every kind of chromosome. So this karyotype represents a diploid cell because there's 2 of every kind. And for humans, the diploid number of chromosomes is 46. Okay, let's come back over here and use a different prefix. If we have 3 copies of every chromosome, that's lethal for humans, but some plants can actually pull it off. And in week 9, we'll go over that. If you have 3 copies of every chromosome, that means you are triploid or triploidee. And so in order to figure out how many chromosomes you have, you go 23 times 3, and that's 69. So a triploidy cell for a human would have 69 chromosomes. Tetraploidy would be 4 times 23, which is 92. And monoploidy would be 1 times 23, which would be only 1 ploid, 23. Now, because we're scientists, we have to be very confusing. And so we actually don't use mono for the ploids. We use a term called hap. So it's haploid. Technically, there's only 1 P, but I don't like saying haploid, so it's haploid. But that means the same thing. Hap would mean the same as mono. It's just 1 ploid. So a haploid cell has 23 chromosomes in it. There are examples of cells in your body that are haploid. The sex cells, the sperm and the egg, are haploid. They have half the number of chromosomes that they're supposed to have, so they just have 1 ploid. So they're haploid as opposed to diploid. And next week we'll learn about why that is. So there are human examples of a haploid cell, and they only have 23 chromosomes, 1 of each of the types, whereas a diploid cell has 2 of every type, so they have 46. Now let's go to this other column. If we go look at this, so this is a diploid cell, but let's come down here to our Down syndrome example. This is where our ploids start falling apart. Because the Down syndrome example, they've got 2 of every chromosome, so they should be diploid. But down here, they've got 3 of this one. So they break the definition of diploid because the definition of diploid is 2 copies of every chromosome. And these guys have 3 of one of their chromosomes. But they can't be triploid, which is the next one up, because they don't have 3 of every one of their chromosomes. So they're not diploid and they're not triploid, they're somewhere in between. So we have to come up with a different term to describe somebody that only has 1 of their sets of chromosome out of line. And that is where we bring in the Somie suffix here. Somie, rather than being multiplication, it's an addition problem, because it refers to only 1 of the sets. So we're saying the number here in the left-hand column only applies to 1 of the pairs. We're assuming all of the other pairs of chromosomes are in their normal diploid state. So because of that, for humans, this is how I like to do these math problems. For humans, we know that our diploid number is 46. So if we're assuming that all but 1 of the pairs is normal, then that means there must be 2 copies of every chromosome, and then we'll ignore the last one and figure out what that is later. So for humans, 46 minus 2 is 44. So we're saying we know for sure this cell has 44 chromosomes in it at least, because all of the sets but 1 are normal. Then what we do is, so that's what Somie means, is it's plus 44, basically, for a human. It's plus 44. And then over here on the left, we just add the number to 44. So, and again, this is where it's frustrating. When we go to Somie, we switch back to mono. I don't know why. Ask some scientist back in the past. So a mono Somie cell would have 44 plus 1 chromosomes, which is 45. If you come down here to my example down here where they're missing a chromosome, these guys are missing a chromosome. They have 45 chromosomes. That is an example of a monosomie. The particular disorder is monosomie X, because they're missing an X chromosome. Monosomie, because they only one of their chromosome pairs has only 1 copy. So there's an example of a monosomie. A disomie is exactly the same as a diploidy. So we actually, disomie doesn't exist. We just say diploidy because if you did 44 plus 2, it comes out as 46 as well. So a disomie is the same as a diploidy, so we just never use the word disomie, we just say diploidy. A trisomie would be 44 plus 3, which would be 47. And that is our case with the Down syndrome kid up here, because he has 3 copies of one of his chromosomes, so he has 47 chromosomes. So he's a trisomy 21, which is the other name for Down syndrome, trisomy 21. And then tetrasomie would be 48. And again, this just depends on whatever creature you're working with. With that plant that has 16 chromosomes, you would just do, rather than 44, you would do 14 and then add the prefix to it. So so if you can assemble this table, determine what the ploid is, then you fill out the right-hand column by using that, and then you take the diploid minus 2 and then add the prefix for the somies. And you'll always be able to figure out how many chromosomes there are in that particular cell. And I'm sorry if that's confusing. It's kind of a difficult concept to grasp. We'll come back and hammer it heavier in week 9 to make it a little clearer. There are 2 terms to add here that are also important to know. The first one, and both of these are just for the ploids. So the first one is euploid. So a euploid cell refers to any cell that is normal, any cell that has its normal number of chromosomes. So for humans, our normal number is 46. So if you're a human euploid cell, you have 46 chromosomes. Notice that's just another way of saying diploid. We're just saying that euploid means normal, whereas diploid, the definition of diploid is you've got 2 of every chromosome. Euploid means it's your normal amount. 2 different terms with slightly different definitions that mean the same thing. The other term is aneuploid. If you are aneuploid, it means the cell is has any number of chromosomes that's not normal. So if they've got 47 chromosomes, or so for a human, if they've got 47 chromosomes, they're aneuploid. If they've got 42 chromosomes, they're aneuploid. If they've got 156 chromosomes, they're aneuploid. Aneuploid is just a catch-all term for anything that's not diploid. So a monosome is also an aneuploid, and a monoploidy is also an aneuploid. Unless you're a sex cell, because a haploid would be normal for a sex cell. So it's a little tricky, but don't overthink it too much. Just remember that euploid is whatever's normal, and aneuploid is anything that's not normal. And then these terms are more specific. So anyway, sorry, that was a handful and a half. Feel free to set up a tutoring appointment with me if you need more help, more explanation with that, or you can talk to your professors, send me an email, whatever you'd like. And we can work through more of these. That's a general overview of week 1. I'm sorry this video was extremely long and a lot of information. Go back. You're welcome to go back through and watch certain parts of it again. Again, this week is a little heavier than most weeks will be. We just have to lay down a lot of groundwork. So thank you for watching. Hopefully this wasn't too overwhelming or confusing. And yeah, have a wonderful day.